Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
I'm a researcher over at Microsoft Research in Redmond, and most of my work is in new forms of input and looking at human-computer interaction in particular, and as well as looking at that from the perspective of facilitating new touch and gestural interactions in mid-air and on various surfaces. So I've done a lot of unusual form factors, as you see here on the screen. But today I'll talk to you about what I really think is a new generation of user interfaces that we're seeing right now come to life. Instead of interacting through indirect input devices, such as kind of typical your mice and keyboards, the users are interacting now directly with the content that they want. So one of the interesting things about this concept and this statement is actually, first, it's direct. It's uninstrumented. You're not going through any device in particular. You might be sensed, but you're not necessarily holding or gripping or manipulating any particular physical device. Second is that there's a change in the way that we think about user interfaces that's happening right now, and that is that instead of interacting through what I called Chrome, which is kind of all the user interface elements, such as the menu bars and sliders and all sorts of things that people are very familiar with, we start to interact directly with the content. Content becomes the interface. If you want to scroll a list of things, you literally scroll the list. You don't take the scroll bar. If you want to access something, you literally manipulate it directly there. And to illustrate this, I think there's two projects that really come to mind that are bringing this to life. And of course, this is really permeating throughout our computing today. So first one is the Surface, and most of you are familiar with this. Can you have the sound, please?
One that reacts to brushes and fingers and everyday objects. Microsoft Surface lives where people gather, where leisure is the rule rather than the exception. Everything happens face-to-face, family style, on a digital table set any way you like.
So this is an old video. This is a couple years old right now, but I think it illustrates what I'm talking about. Is the fact is that when Surface was started, and the lab that I come from actually has a lot to do with that particular work, the whole idea was to transcend the notion of whatever is current interfaces and current Chrome around the interface, and make the content the focus of interaction. I think similar stuff is happening right now with Kinect. If you actually look at this again, another promo video.
So, you've come back for more.
Yep, let's do it.
This should be good. Let's begin.
You can make this turn.
I'm going in.
Okay, I'm ready.
Okay.
Very good, awesome.
Come on, hurry up.
Okay, go, 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 go. Bonus points right here. You got this.
All right, you'll see probably a lot more Kinect videos today, so I'm not going to play the whole thing. But in general, these are two key points that I want to make, is that the interaction is really becoming direct, and the content is the stuff that we interact with. In some sense, you can think about this as these interfaces really are starting to bridge the gap between the real and the virtual worlds. They're starting to merge those together. Your physical actions, what you do directly, has a physical manifestation in the computer interface. However, most of these interfaces are still confined to the rectangular screen. You're still experiencing them in a remote setting. It does give you a sense of immersion, but it gives you a sense of remote immersion. So what I'm going to talk to you today about is this opportunity that we've seen and we are exploring here to use a depth camera and the projector as a unique combination to enable interactivity basically on any available surface and between all the surfaces, basically to enwrap you and envelop you in interactivity, and anything that you touch and any available surface in the environment can become interactive. So to kind of illustrate this point, this is an older video from a colleague of mine, Andy Wilson, which used the depth camera above the tabletop to simulate how would it be to literally be able to place whatever object you want on tabletop and then play a game directly with that. So this is a form of augmented reality, but it's purely projected. There is no instrumentation, except the instrumentation is kind of hidden in the room. So what you're seeing here is, this is kind of a virtual view. Anything that you place on the table actually becomes an obstacle, and you're literally running a little driving game over that. So the system does not know anything about the red object or the green object or anything like that. It's just basically giving you terrain, and this is all facilitated through the depth camera used above the table, and combination of that with the projector. So here you see a little bit of interacting with kind of doing some pinching and creating new objects, and then you're really taking full advantage of physics-like interactions and simulating the real-world physics. One of the things that people often did in this particular system is you always wanted to reach in and kind of try to actually grab an object, and so here you see some early attempts at that, and I'll explore this concept further on in the talk. So one fun thing is to try to drive the car over your hand. So as I mentioned, this is basically augmented reality, but it's augmented reality in a different take. People often think about augmented reality and virtual reality, and you think about lots of gear. And this is actually a picture of me a couple of years ago. I did my PhD on augmented reality topics. And oftentimes you end up having lots of gear. You have trackers, you have head-mounted displays, you're having, these days you can do a lot of stuff with smartphones, etc. But it's always through some sort of screen. What I think about this is a form of spatial augmented reality. It's in some sense deviceless to the user. They don't really bring anything new. They don't have to interact with anything. And it's high fidelity. I want to enable full dexterity of your hand and full dexterity of all of your interaction capabilities to interact with the content. So before I go, I'm just going to give a brief overview of what the depth sensing cameras are and the basic types of it, just to kind of ground this exploration. So basically what I mean by depth sensing cameras is the cameras that actually report a color image, like an RGB image, and a depth per pixel. So for each pixel in the image, you actually get the range data of how far that pixel is from the camera. So what you see down here is basically the output of the some depth camera, where you see the RGB data and you see the depth data there. So there are three basic types of depth cameras that are mostly available today. So the first one, and the most common one, I guess, is the stereo approach. There's a time-of-flight set of cameras, and there's structured light set of cameras. So the stereo approach goes like this. You basically have a two-camera system. They're fixed distance. They're mounted on the same bar, basically. And there's several companies that make them commercially, so they're available for purchase in many ways. But the basic premise there is that you have two different images of the same scene. So if you have a left and right image, as you see here, if you have an object in the middle, you're going to see it differently in the left image from the right image, right? And so this difference, the difference between two images, as long as you can correlate that this is the same object, gives you a way to actually triangulate and figure out the distance. So if you move, the objects are going to move in two images, and again, you're going to be able to compute the distance of that particular object. Now, in principle, this is super simple, but in practice, it actually requires very good texture to be able to match between the two different objects, to be able to latch onto it and figure out the correspondence. It's actually computationally intensive, and a fine calibration between cameras is required. Oftentimes, it's also problematic with occlusion, so different cameras see different things, and you get a lot of noise if you're just doing this naively. But anyways, this is definitely a plausible way of obtaining depth. A second line of cameras, of depth cameras, are time-of-flight cameras. And I'm showing one example here of the several years old Israeli company 3DV camera. And the basic premise of time of flight is actually what it sounds. It actually times how long the flight takes from the camera to the object and bounces back. It measures the amount of light that gets reflected. So these cameras usually consist of a camera, infrared camera with a solid-state shutter, like a really fast shutter, and pulsed lasers around the side, and as well as the RGB camera to get you the RGB image. So there's a couple of manufacturers that used to make them. There's still a couple of them on the market for those who are interested. But the main idea is something like this. You actually pulse a lot of light. That light is shuttered, so you only have a certain amount of that light going into the environment. This is usually infrared, so you don't get to see it, but the camera sees it. When that light hits a person or whatever object in the environment, it actually gets reflected. The closer that object is, the more light gets reflected in the specific time frame of the camera. So you can actually correlate directly the amount of light that gets reflected to the distance of the object. The more light that comes back, the closer the object was. And you see that here in this image. So if you think about that as being a grid sensor rather than a line sensor like I'm showing here, you actually get an image. And this is the same image that I showed before. So lastly, this brings me to the structured light approach. And Kinect is one example of structured light cameras. The way that Kinect works is that it has an infrared projector, an RGB camera, and an infrared camera. So it's based on a PrimeSense design. PrimeSense is a company that actually made the reference hardware for Kinect. And the main idea here is that it overcomes some of the problems of stereo because it provides its own texture. The only purpose of the infrared projector is to basically project a known texture into the environment, and it's an infrared texture, so nobody sees it unless you actually look with an infrared camera, in which case it looks something like this. So it looks random, but it's not completely random. It's pseudo-random for that particular camera. And the notion of actually knowing exactly what that pattern is what makes this computation possible. So in reality, what you do is you project a known pattern into the environment, and you sense that with a camera that's slightly offset. Now, since you know what the pattern should look like at certain distance, you can actually figure out how it's distorted. And if you know how the pattern is distorted as you go through it, you will actually figure out what the disparity is, and the same principle as in stereo, you can basically triangulate the distance. So having a particular pattern is actually super beneficial because now you're suddenly not depending on the texture of the objects in the environment. You can actually look at the white shirt, or you can look at the different objects in there, and you're presenting your own pattern. You basically simplify some of the matching process. So here's some of the kind of characteristics of the Kinect camera. But I think the most interesting one is that it finally brought down the price. This is now suddenly available to a lot of users at a very reasonable price. Most of the other cameras that are thousands of dollars at this point, because they're they're at some point research prototypes. This is now mass manufactured, so it brings this technology to the masses. So why sense with depth cameras? Remember, what I would like to do is enable interactivity everywhere and enable both interactivity on the surface and above the surface. So the depth cameras gives you the opportunity to provide no instrumentation to the user, but actually remove the instrumentation, put that into the environment. And it also simplifies the understanding of the objects in space. That's how the algorithm that actually detects skeletal tracking works. It simplifies the extraction of your body and contours and matches that to the skeleton. So let's go to the next project, which basically used 3 depth cameras to do exactly that. So we constructed a system called Lightspace. And this was shown last year at several events, in which we grouped a combination of a couple projectors and couple cameras, couple depth sensing cameras in the ceiling of one room. So we constructed this particular room, but basically it's a combination of 3 projectors and 3 cameras. And I'm going to show just a little video of what is possible with Lightspace.
Lightspace explores a variety of interactions and computational strategies related to interactive displays in the space they inhabit, touching on aspects of multitouch interactive displays, augmented reality, and smart rooms. LightSpace uses 3 PrimeSense depth-sensing cameras and 3 standard projectors. These are arranged to cover most of an office-sized space and are precisely calibrated to real-world coordinates of the room. This results in a fairly complete 3D mesh model of the room and its contents, complete with moving users. Because the projectors are calibrated to the same real-world coordinate system as the cameras, it is straightforward to project graphics of the correct size onto any surface visible to at least one camera and one projector. Furthermore, experiences are authored in real 3D coordinates without regard to which camera or projector is ultimately used. We use this basic infrastructure to explore a number of interactions on, above, and between interactive surfaces placed in the room. First, the user may view and manipulate virtual objects on this tabletop, which is just a regular desk. Also, there is a wall display that functions similarly. Here, the surface is just a piece of foam core. Beyond simulating the behavior of interactive displays such as Surface, we consider interactions that involve the space between surfaces. For example, our user can move an object from one surface to another by touching the object and the destination surface in that order. An object may also be picked up by sweeping it into the hand. The object is depicted as a sphere that can be held and rolled in the hands and arms. The object may be dropped on this piece of cardboard and handed from one person to another. The held object can be dropped directly on an interactive surface. It may also be placed on an interactive surface by touching the destination with one hand while holding the object in the other. We have also implemented a menu that is organized in space. The spatial menu is invoked by holding a hand in the column of space directly over the menu graphic on the floor. Menu selection changes as the hand is moved up and down in this column. Note that the text of the menu is oriented toward the user for easier reading. The menu item may be selected by pausing briefly at the selection. Finally, we show how LightSpace can highlight each user with different colors. When 2 people touch, they are considered the same object and are now the same color, and can even participate in the same interaction.
So there are a lot of different interactions here, and I'll go through some of them to basically highlight how we implemented this particular system. So LightSpace consists of 3 different projectors and 3 different depth cameras. These are PrimeSense cameras. This system was actually done prior to the release of Kinect, so we used the reference cameras in our explorations. And what you see here is actually the view from these 3 cameras. Now, the reason why we use 3 cameras is not that that's some sort of magic number. Is basically we use cameras to extend the visible space. So we just basically tile them up with some small overlap to get more space. And you can think about our system in the ceiling as basically one big chandelier that has a depth camera and a big projector that's kind of omnidirectional. So that's kind of what we are going for. So the first thing that we did is that we actually combined all these cameras, we calibrated them together, and we combined them in a unified space. So this space, actually what you're seeing here is the view from 3 cameras above, and each of these cameras is fed into one unified 3D system. This allows you to actually reason and author and do all the stuff in this unified space without necessarily worrying which camera is seeing it and which projector is projecting it. So how does the calibration work? Really what you need to do is you need to calibrate all the projectors and all the cameras with respect to some sort of real world, right? So this is done once, and then the system basically runs on the ceiling for as long as somebody doesn't touch it. So in order to do that, you place a camera somewhere, and you look, for example, at the desk surface, and you place a couple red reflective markers on it, just something that you can actually easily spot in the camera image. If you know where those markers are in the real-world coordinates, you take a measuring tape and you actually just measure out where those places are. You can actually, in addition, and you know additionally the intrinsic parameters such as focus, and the resolution of the camera, you can actually figure out all the necessary transformation that places that camera and orients that camera in space. So it becomes basically you turn the reporting of that camera into the world coordinate space. You do the reverse actually for the projector. So for the projector, you also look at the same space, but this time you actually have to correlate the projected points to those markers as well. If you do that, and again you know the intrinsic projector parameters, you can figure out the calibration transformation for each projector. And this is repeated for each projector, and once you do it, as I said, it basically is fixed. So what this allows you is that you start being, with the camera, you start being able to track any movement, any object in real-world coordinate space. So if you move your hand, you can actually simply track it. But also, if you want to project something on that hand, you don't have to necessarily worry about what distortion it's going to be. All you have to specify is where in 3D space it's going to appear. And as you move your hand, the projector will actually account for, this calibration will account for the deformation that it needs to happen in order for it to appear correct size, let's say, in your hand. So this allows us to do all the authoring, all the experiences and interactions in real-world coordinates. So you can literally say, something is going to be 2 meters off this podium, let's say. And it's irrespective of which camera it is. It's irrespective of which projector it is. All it takes is just saying, it's visible by some camera and some projector. The system will take care of it. And that really frees you up from having to think about in standard terms the way that we author environments, and you can start thinking about them in physical terms. You can start saying, I would really like a menu right here, and I'd really like something else to appear between here and there. So let's move on to how do we actually support some of these rich interactions. One way to do it today would be to actually use the skeletal tracking from Kinect. So in that sense, skeletal tracking gives you the joints positions of your body, and it tracks there. But the problem with that is that it's really view dependent. If you try putting Kinect really high up above your head, or if you try doing something else, it's basically designed to have a front-facing view, and it can only handle about two simultaneous skeletal in the scene, users in the scene. So we want it to be much more extensive. We want it to be much more in some sense, not really tied to this particular representation, but any kind of interaction to facilitate real-world interactions in our space. So what we do is we actually use the full 3D mesh gathered by all of these different cameras, and we try to preserve some of the analog field through physics-like interactions. So we're actually simulating interactions directly on that mesh. And whenever possible, we actually reduce some of our reasoning and about the space to 2 dimensions rather than 3. And I'll show how that's possible. So here's an example of what I mean by interacting directly with a mesh. You're actually seeing here the interaction of this. This is just a circle, virtual representation of an image in my hand. And all this is doing is actually in 3D space is just represented as a ball that actually has a physical representation, right? So it actually it's manipulated by the mesh. You're seeing it as a 2D projection, but basically it's represented as a 3D ball, which has some pseudophysics behaviors. What I mean by reducing the complexity is the reasoning about 3D mesh in space is actually quite complex. The algorithms are complex, the connectivity is complex. To actually do this is computationally really intensive. But one thing that you can do with these, with our space, is that all of a sudden you can create virtual cameras. Basically, you are limited to 3 cameras that you have, real cameras, but because you have depth data, you have 3D points in space, you can position virtual cameras wherever you want to, and you can make them however you want to actually look at data from different perspectives. And this is exactly the concept that we do. So to simulate interactions on the table, we literally make a virtual camera which contains the real depth data above the table in this little slice. So it's basically an orthographic projection down looking above the table. And what you're starting to see is that the data that comes in there from my hands looks remarkably similar. If you're familiar with surface computing, this looks remarkably similar to what you would expect in Surface. The same thing goes for the wall, right? You get the wall and you actually see your hands directly interacting there. You can also take a slice, kind of a big slice through space, and combine all the cameras top down, in which case you get kind of an orthographic space view, right? You get everything from top down. Now remember, there is no actual view, real camera view from these projections. These are orthographic cameras. They don't exist in reality. But they do. It's very easy to synthesize those views, and then you can start doing a standard kind of 2D processing, connected components and tracking in 2D, which is relatively trivial these days, to reason about the 3D space, because all you need to do is position some of these projections accordingly. So So this really allows you to do something like this, right? You're literally simulating having a virtual surface directly from the table. And if you look at that in 3D, it looks exactly the same. This is the virtual view of the same interaction. This is the real depth data and the table and the data projected on it. Excuse me. Okay, another thing that we wanted to support is we wanted to not just be confined to the surfaces, but actually be able to move objects in the space and interact between the different surfaces. So one thing that you need to do that, you need to figure out what's connected to what. If you want to establish kind of these body connections, like I touch here and I touch the wall, you need to actually understand that the same touch on the table corresponds somehow in 3D space to the wall. And we do this exactly through this space view. If touches are connected in this top-down view to the same body, they actually are. We assume that they are actually part of the same connected component. So this allows you to do something like this with a little sound effect. What this also means is that the physical connectivity is actually a property of real connectivity. It's not necessarily based on some sort of skeletal matching. All it is if there is actually a connection between a point on the table and somehow goes through space, it can be through multiple people, and it touches another object, you can actually complete this circuit and do the correct computation. Another interesting idea is that now you can start situating objects in space where you don't necessarily have a surface to project onto. You can use your body as a projection surface. So literally, for example, this menu is nothing more than when you place your hand in surface, you get an option there. You just move it up and down, you get a virtual menu. The way that it's implemented in 3D is literally you look at the 3D data above a particular point and you do it. There's nothing really complex about it. But what's interesting about that is that you can, you know who is operating the menu. You know how they're placed in space. And you can orient the text. You can do all sorts of neat tricks to the menu itself by just knowing who's really operating and where they're looking from and how they're accessing it. So this was our kind of a first implementation of this, and I just want to make sure that people understand there's a lot of other implementations of smart room and ubiquitous computing in the literature. We're really building on this, but this is the first one that actually uses depth cameras, and we believe it's kind of the most complete implementation so far. But what's still missing? In light space, the touches were really kind of hand blobs. Like really, it was very crude approximation of what a touch representation would be. Ideally, you would like to have something like multitouch. You would like to have surface-like behavior, so you would like to do the same things that you can today do on an iPad or a smartphone and things like that. Also, all objects were literally constrained to the surface. All objects, even if we represented them as 3D, they were ultimately just 2D objects. Ideally, you'd want to interact with 3D objects. If you actually have a 3D object, you want to see it in 3D. And also, the manipulations are also quite coarse. Everything is relatively rough. We want to get full dexterity of your hand. You have all the data. You need to be. We want to be able to use the dexterity of your finger to actually manipulate some of these things. So let's first look at this touch on every surface problem. If you're thinking about it with depth camera, especially depth camera from above, you really have the problem of the two thresholds. You need to worry about the noise coming from detecting the surface itself, which is the surface noise on the left. And you need to start thinking about how thick your finger can be so that you can figure out when you're close enough to the surface that you can trigger this event. So there are these two thresholds that you need to basically establish. And then one approach to actually getting the surface distance and where you think the surface is to do it analytically, which is exactly what we did in light space. What I mean by that is you actually decide that surface should be at this location, and you kind of analytically say, you know, it's this way, it's oriented this way, but this results in a lot of problems. You have variations in the surface flatness. No surface is ideal. You also have problems with the calibration of that. You have lens distortions, all sorts of noise in the image that you're not accounting for. The other option is to really do this empirically, so actually go ahead and measure it. And we did exactly that. You can take per pixel statistics of the empty surface and figure out exactly the noise characteristics of that entire surface, every single pixel there. Just some things for folks who might try this at home. Noise coming from the depth camera is not normal, so you need to kind of account for that. And it's not the same at every pixel location, kind of radially as affected by the lens. So basically you have depth dropping with distance, and you also have with distance increase of noise. But one thing you can do is actually at every single pixel you can build up a little histogram. You can actually just statistically accumulate a lot of different values that the depth camera tells you. So you can think about this as having at different levels above the surface, I'm getting this many readings over some period of time. And then you can determine once you actually see a nice drop eventually where that histogram falls off. This can give you basically the good representation of what your surface noise is. And in order to make some assumptions about how thick your finger is, you need to start thinking about what the anthropomorphic values of your finger is, like how thick can it actually be, and what the noise level is at that particular depth. But anyway, here's some rough numbers to kind of give you a baseline. We did some extensive experiments to figure out what's the best case scenario, what you can do. And if you're 0.75 meters away, 75 centimeters away, so you put a depth camera about 75 centimeters above the surface, you actually get the surface noise to be only about 3 millimeters, so you're really able to resolve quite low numbers. And the finger threshold can be basically 1.5 centimeters, so you get very precise touches. At 1.5 meters, you're slightly off, and there you get a 6 millimeters and 30 millimeter finger thresholds. The way that looks is take a look in this video. So literally what you have is just the view of the table from the depth camera, and you're seeing just the side view of a camera just to show you how it actually works. So if you do this histogramming, and if you do the surface, you're actually starting to see the fingers only being captured in the image. And now that image, you can run a low pass filter over it, and what you're getting is something remarkably similar to what Surface device would give you. So you can easily track these as connected components. But fundamentally what this gives you is more than just surface. Now any kind of object, because you can take empirical measurements about any object, you can do touch on any kind of deformable object. You can do touch on a sphere, on any curvature approach. And it's fairly reliable. You get per pixel accuracy, and it roughly depends on the distance of that depth camera to the surface. So this shows you how you can actually approximate surface-like behaviors, multi-touch on the surface. But if you notice here, all the surfaces are static. We're not moving anything yet. And that's a big problem. If you want to interact in real world, if you want to interact in space, most of the things that you interact with, you want to kind of be able to move without having to recalibrate. So one thing that you can think about is how would you allow touch on any dynamic surface? And the solution that we came up with is that you actually have to do two things. You have to dynamically calibrate the surface. You need to track the surface in some sense and try to infer its statistics, its noise statistics on the fly. The other thing is you have to start thinking about what the finger really is, and you have to start tracking this higher level construct of a finger and starting looking at the posture. What I mean by that is you have to start figuring out where in space is your fingertip, let's say. I'm going to give you one example. We just completed this work this spring. So this example uses another depth sensing camera. This is a shoulder-mounted system that uses a pico projector and a depth camera just mounted on your shoulder. And the whole idea is this is supposed to be very mobile. But this is an intern of mine, Chris Harrison from Carnegie Mellon. And what you're seeing here is actually, this is our example of touch on every surface. So this is a highly deformable surface. It's a hand. It's not regular in any way. It moves however you want to. It has all the stuff. But you see here the system is actually reliably tracking, not only tracking, but it gives you actually a hover space over this particular surface. And it's continuous. It doesn't really care what the surface is. You can move the hand in and out. All it is, the magic here is, again, the depth sensing camera and the projector. So it's kind of fun to play with this, but I'll just give you one little example of what you could do with this if you have this possibility. So you can start thinking about what would it look like to have a phone literally be your palm of your hand, right? You slide to open, you dial a number, right on your hand, and then maybe you have a Bluetooth headset that lets you talk, and you're literally talking on your phone right now. You don't need to carry an extra device. I mean, there's all sorts of other opportunities that you can do with this, but this is just a preview. I mean, more stuff is going to come when this publication actually comes out, but the idea there is, again, any surface, anything can be multi-touch and interactive in a real way. All you need is a depth camera and a projector. All right. This is exactly the point that I just made, so I'll just go to the next slide. Let's go think about the second part of what I was initially talking about, which is now you want to interact with 3D objects. In micromotorcross, the first game that I showed you with car driving simulations on the tabletop, and in light space, all objects are basically planar. Nothing really stands up. Nothing is really 3D. Nothing really has volume. And if you want to, you can start with thinking about how would you actually hold a virtual 3D object in your hand. But before we do that, let's take a step back and start thinking about how would you interact with it using the full dexterity of your hand. How would you actually simulate having multiple fingers and manipulating it? So one thing that helps you is if you know the geometry of the world, you can simulate. You should be able to simulate how the physics actually respond to it. Why I say should be is because even if you know the geometry of the world, you don't actually know all the characteristics of the world. You don't know the surface properties of the world, and you don't know the masses that are involved with forces. So if you actually think about physics and the real world physics, kind of Newtonian physics, you are not able to simulate all aspects of it, but knowing geometry brings you a long way forward. Luckily also, there's commercial packages, there's physics game engines that are commercially available that are basically solvers. They're constrained solvers on a large scale that are very highly optimized for doing these computations at high dimension spaces. So you can actually get the use of all the GPUs and CPUs acceleration for these game engines to let you perform real world physics on objects. But the problems are that if you think about the output from your depth camera, it's basically a dynamic mesh. You get a mesh that changes at every frame. And dynamic meshes are not supported really in physics simulations. All the physics simulations assume rigid bodies because in reality, it's hard to extend something and hard to compress something without changing the physicality of that property. You're changing the density, basically. So the real way to think about depth sensing cameras, I like to use the metaphor of pincushion toys. So the only thing that really comes up is in and out. You don't get any lateral stuff. You cannot place a torque. You don't get anything like that. No information like that actually comes out from the depth camera. Also, what becomes really hard, because if you think about pincushion toy, it's really hard to grasp something. You cannot actually hold something by that because you're not exerting any lateral forces. You're not making any movements in and out. So these are the problems if you actually want to use physics to approximate interacting with 3D objects. And here's the first take that we did a couple years ago. So instead of representing objects as a deformable mesh, we're actually representing every single object in the scene with a bunch of proxy particles. And this system actually allows you to quantize all of your objects. So what I mean by proxy particles is you represent your hand literally with a whole bunch of spheres, for example, in this object. And you're seeing here my colleague Andy basically juggling a virtual ball. Now notice that he's barely able to move it around. He's not able to exert lateral forces. We did that later on, and I'll show you how. He has to kind of cup it around and move it slowly. And also interpenetration is quite difficult. If you actually go here and interpenetrate the object, it's going to start, the physics is basically going to be insolvable, and you're going to start having some really large force. So you have to account for that. But this very idea of that you can represent your body and any kind of object with a proxy particle solves a fundamental problem for using these physics engines. Basically, it allows you to represent a dynamic mesh, not as a dynamic mesh, but a representation of rigid bodies. So now that you can kind of start seeing how you could potentially interact with it, can you actually see the thing in your hand? Right now, everything is still constrained to the screen in this particular example. And seeing 3D has been explored a lot in the VR literature and the AR literature. But in summary, there's basically many cues that give you the 3D perception. The cues are kind of in increasing order of importance would be the size. You know, if things are bigger, they're closer. If they're further away, they're smaller. It also gives you the occlusions. If things occlude, you know what's in front. The shadows are a good indicator of the 3D perception. Motion parallax is especially a fine one, where you actually, if you move your head, you get to see different perspective. The things at different depths move at different speeds, as well as stereo. Stereo is just one of the cues. And one other one that's eye focus. Your eyes actually tend to focus at the different objects, as well as they converge on a different object. They basically rotate in their eye sockets when the objects are close or near. Now, some of them we can actually simulate today. The focus and convergence are hard, but you can simulate the first 5 if you know the geometry of the scene and the user's viewpoint and their gaze. And guess what, again, if you have the depth camera, that's actually quite trivial. Figuring out the geometry of the scene and the user's gaze point and viewpoint, you can definitely do that. It's very straightforward. So what you see here is an example of, this is actually taken from the Mirage Block demo, but this is an example of literally you holding a ball in your hand. This is correct only from your perspective. But everything that's enabled there is, again, simply enabled with one projector, one Kinect camera in the back, and if you want to see stereo, just put stereo glasses on. Those are basically shutter glasses. They're not tracked in any way. They're just literally shutter glasses. So the camera here does a dual purpose. It basically allows you to track your head. You need a head position, but it also digitizes everything that happens on the surface, right? It gives you the geometry of all the objects on the surface. I want to stress, because you're giving correct perspective views, you're necessarily limited to a single user experience, right? So in many ways this is very limiting, but for you who's currently looking at the perspective, you get the left perspective. You see the object in your hand, and you actually see part of that ball being projected correctly, given your geometry, given your hand geometry, correctly projected on your hand, and part of it being projected behind, being occluded or something. So when you look directly in there, if I was looking here, part of it would be here, and part of it would be way in the distance on the floor, let's say. To the third-party user, somebody looking from the side, it doesn't look anything correct. It looks actually distorted, as you see here on the image. And if you combine that with the proxy particles that we saw before, here I'm just representing these particles back into the scene, you end up having a fully functioning 3D visualization with full dexterity system.
In Mirage Blocks, a 3D stereoscopic projector projects virtual content directly on top of the real world. The 3D information is captured by the Kinect camera, which also tracks the user's gaze. This enables presentation of correct perspective views to a single user on top of the dynamically changing geometry of the real world. To simulate physically realistic behaviors, all real-world objects are represented with proxy particles, in our case spheres, which are dynamically updated and used as collision geometry in the physics simulation. This allows the user to use any part of their body or any other real object to interact with virtual content. In addition to supporting direct interactions with virtual content, depth information can be used to instantly digitize the real world and then interact with such recordings. For example, the user can digitize real bowling pins and play with them in a virtual bowling simulation.
Right, so all of a sudden with this system, anything that's physical, anything that has geometry and shape and occupies some volume of space, you can convert into a digital representation. And not only that, you can actually use the representation to interact with other objects. You can use the representation to simulate interactivity, to do this high-fidelity interactions. So we are we're investigating lots of different applications for this, and one of the obvious ones is telepresence. You want to have a shared workspace with somebody remotely. What's virtual to you is actually physical to them, and vice versa. So you can actually kind of have a shared co-located space. But another interesting thing is now this opens up a whole set of augmented reality applications. Think about, for example, online shopping right now. If you buy a book, it's great. You know exactly it's going to be a book. But if you buy, let's say, a watch or a necklace or something like that, or a shirt, right now you don't really know how that's going to fit you. How is it going to look on you? With a system like this, you can so easily overlay whatever you want onto your real body, or whatever whatever other object you want to. So if you want to see how the watch actually looks on your hand, all you have to do is stick your hand right in front of the projector. You see exactly how it looks correctly to you in 3D there. Now you're at the mercy of the 3D projector, the resolution and the noise of the camera. But with improvements in that, I feel like you're definitely being able to get a pretty nice immersive experience there. So I'll just briefly mention one more thing, grabbing. I haven't talked much about it, and primarily because it's a super hard problem. You don't have any lateral forces, so you kind of have to infer a lot. You have to do a tracking a lot. So here's a little preview of what grabbing could look like, and this is very preliminary yet. But I think the safest answer to that is we're still working on it. I think we'll solve it, but it's quite hard. But that's ultimately what you would like to do. Like, not only you want to hold objects, you want to grab them, move them, and again, with full dexterity of your fingers. This particular approach requires you to actually track things frame to frame. You need to know the correct correspondence of all these particle proxies. So in summary, I believe that the combination of a projector, 3D projector, and the depth camera, I'm showing Kinect, but it can be any depth camera, is actually quite unique opportunity right now for new user interfaces. It can enable you to do interactivity anywhere you want, all around you, anywhere you want. It can basically turn your room or your body or any object as an interactive display surface. I showed you how to do reliable touch, almost as good as real touchscreen quality touch, just using depth cameras, and as well how to do 3D interactions on that. And lastly, because you're capturing the full dexterity of your fingers, you're actually having very analog, very physical interactions. You don't have to necessarily learn them. This is the stuff that you learn when you're 1, 2, and 3. You're starting to grasp and hold and figure out how to manipulate the physical world. You can translate everything like that into this experience. So the demo of Mirage Blocks I brought here, so they'll be here tomorrow, and you can come by and see the demo. What am I doing on time? Okay, I'll show you just briefly a couple of resources for folks who are thinking about doing some of this in their own research. One thing that there's probably going to be more talk about, Kinect SDK for Windows is coming out. Stay tuned. It'll offer a lot of skeletal tracking, and as well as the array microphone and all this stuff. You can find more information on the website. The physics game engines are readily available, and they're actually free. There's two pretty powerful ones that we've used in our research, and I've highlighted them here. They also have many wrappers over them, so you can have your Java wrapper or C# wrapper or things like that. Also, if you want to do 3D stereoscopic view and stereo glasses, I think the simplest solution right now still is using the NVIDIA system, the 3D vision. But there's interesting technologies on the horizon. We've used DLP Link, which is kind of cool because there's no emitter there. The emitter, so the emitter for the sync signal for the glasses actually ends up being embedded between the two frames of the DLP projector. So every time that you look at anything that's being projected, you have a correct signal. It's quite an interesting technology, but it's still kind of hard to get. As well as these are my collaborators for some of the projects that you saw today. And at this point, I'd like to open up the floor to some questions. Thank you. Yes?
In your opinion, how far are we from the now hypothetical situation of giving talks remotely?
Sorry?
In your opinion, how far are we from the now hypothetical situation of giving talks remotely?
Well, in some ways, I think we are there, but how compelling the experience is, it's up for debate. I mean, one could think about video telepresence as being some sort of telepresence that gives you an impression of something like that. I guess what you're referring to is kind of full 3D holographic remoteness, right? And I do believe that we're still fairly far off from fully immersive, high-resolution, high-fidelity kind of telepresence in that sense. But I think we're making progress. If you can assume certain things, where the audience is coming from and what the viewpoints and things like that, I think the problem becomes easier. But in kind of general sense of having people around and you're having just mid-air display, I think it's fairly hard. Right now, I think you kind of balance. For compelling experiences, you balance two things. You balance being able to be viewed by many and having a highly realistic, high-fidelity experience. So if you want many people to be able to see you and experience you simultaneously and easily, then you tend to go with, right now, still the solutions that are best are the 2D solutions and video and things like that. But if you go, you can't simulate very compelling experiences as long as you're kind of tracking a person and providing personalized views. That ends up being quite compelling, but again, that's only for a single person. There's there's a microphone.
Good. Thank you. Nice talk. Thank you.
Thanks.
I was wondering, how do you deal with the problem of control when you are interacting and when you don't want to be interacting in the same environment?
That's a great question. I think I like to think about it as Midas touch problem, right? If you live in 3D space, and if you suddenly enable everything to be interactive, then how do you disengage yourself from the 3D space? Is that kind of what you're referring to? Well, I think a couple ways. One way is that touch. If you think about touch, it actually has a natural way of disambiguating that particular problem. So if you constrain a lot of interactions on surfaces around you, then people are very good at knowing when they're touching the surface and not, when they're engaged and not. So in many ways, some of those problems goes away. In 3D space, it's slightly more difficult. What we ended up doing a lot of times, if things were just placed in 3D space randomly, like for example this menu, like a virtual menu in space, what we did is we did subtle UI cues, highlights. We projected kind of a virtual shadows objects. So whenever there was a menu in space, there was actually a little projected a menu logo kind of circling on the floor. This gives you a hint that something is above it. The nice thing about really thinking about it in complete 3D geometry is that you simply walking through the menu are not going to trigger anything, because a lot of these things are kind of triggered on a little bit of a hover and dwell. So if you need to be at the correct distance and correct depth and correct and wait a second or something like that at that particular depth for menu to trigger. So if you're just simply walking through it, or if you even if you're standing in the particular menu space, the chance of your head being the correct menu height is low, right? Most of the menus are kind of a hand height, so you're not necessarily just kind of going through it. You're not going to actually trigger it. But I completely agree with you. It's a very hard problem, and the only real answer is that I think you have to solve these things through kind of careful user interface design rather than sensing tricks per se. Go for it.
I agree. Great presentation. Thank you.
Oh, thanks.
My question is, in the light space system, would it make sense to have stereoscopic projections so you would actually see the objects through shutter glasses or things like that? And how will you go about doing that?
Well, so Mirage Blocks is actually built, it's an extension of light space in many ways. It uses same underlying architecture. This time we just designed it so that I mean, remember, in light space, the reason for 3 projectors and 3 cameras is, again, it's not because 3 is a magic number, it's because we just wanted to have larger space. So Mirage, you can think about Mirage Blocks as being the same thing, except it's just 1 projector, 1 camera. Now, in this one, we just replaced the projector with a 3D projector. So it's a 120 hertz, basically a 3D capable projector, and then you can do this. So you can think about our recent work as basically trying to do exactly like what you're saying. So do the 3D, but what you give up, what you have to understand is that light space works for 6, 10 people in that room, no problem. Mirage Box is a single person demo. So everybody else who sits around, they get to see what's going on, but they don't get nearly the right perspective. They don't get the right feeling for what's going on as the person who is actually tracked by the system.
Again, thank you very much for your talk. Very nice. Maybe just probing a little bit further, I think. It's very nice to give a visual impression of what's going on. But when you come to the actual tele-immersion, what can you tell me about the feeling of touch?
Right.
Okay, is there anything going on about it? And
yeah, so I think what you're referring to is haptics, right?
Exactly.
Haptics, yeah. So it's a great challenge. I think it's problematic in many ways. I actually believe that haptics is the next big wave of interfaces that are going to happen. I personally am not involved so much in the research of haptics, but there's some interesting devices already on the horizon. For example, a couple years ago at SIGGRAPH, people demoed ultrasonic haptic devices that are basically able to direct beams of air and focus them in a particular point. So as you move around, you can actually feel a little bump in midair here. And they can focus it particularly at the point. So if you're moving above it, you're not feeling it. If you're moving below it, you're not feeling it. But when you're moving directly over it or above it, you can start feeling it. Simulating force is hard. And it requires energy, right? It requires you to somehow actuate, and that's problematic. And I don't know exactly of a good reason for it. What we've tried to do is try to go to the furthest extent possible to complete the simulation without necessarily tackling the haptic problem. But I do feel like that some of the haptic feedback is really key to some of these things, especially where it really comes down to for us is the grasping part. The grasping itself is not that hard as long as you don't interpenetrate. But the problem is that people never know how far they have to move their hand to really grasp. So really grasping, all of the grasping problem for us is figuring out how much they interpenetrated the particular object, right? If you're trying to hold this glass, but the glass is virtual, you're not going to hold it exactly like this. You're going to try, but chances are your fingers are going to fluctuate, and they might be actually inside the glass or outside the glass, right? But so all the problem for us is basically figuring out how to correct for that and how to account for that so that we're not actually shattering the glass or trying to do something like that. But I agree with you. Haptics, I think it's an unexplored area in human-computer interaction in general, and I think much more will come in that space. But unfortunately, I'm not the expert, so sorry. All right. Well, thank you so much for your time, and thanks for coming so early in the morning.